So, hello everybody. I'm very glad to open this session today. This will be through. My name is Sandra Klinge and I will chair this session and simultaneously actually I will be the first presenter in this session. Up to now we have only two presentations which are saved on the laptop. So if somebody has presentation, then he can come thereafter or before his presentation so that we can save it. Now I will start actually with my talk, which is actually a kind of review of our most recent work on the application of the neural networks for different solid tasks. And so for this purpose, I choose three very different examples. For the first, I will tell something about the application in intelligent mechanics, thereafter for the solution of wave equation, and the last example is related to this evaluation of effective values for heterogeneous materials. Let's start actually with the modeling of damage as a basic model for simulation of this phenomenon. We took the so-called deep energy method, which is nowadays already established as a counterpart for the finite element method. And you can see here the structure of deep energy method. The main part is neural network. It can be fully connected neural network. The input of this neural network are coordinates of so-called collocation points, and the output are suggestions for the displacement of these collocation points. Why I say that these are candidates or suggestions? Because in a kind of post-processing, this displacement have to be adapted to the flare boundary conditions. And the second special feature of this deep energy method is actually the risk function. It is not as usually mean square error function, but it is the potential, as we know that from the finite element method. And for this reason, actually, the similarity of the names, you can see here, we call this method deep energy method. We have to minimize the potential, but now not with respect to displacement, as is usual. We have to minimize that with respect to the neural network. So obviously, if we have some material or the kind of deformation which is which can be described by some potential, then we can couple two of them. And one possibility is, of course, to couple deep energy method to the so-called phase field method, which has been used recently for modeling of damage. In this case, the potential consists of two parts, elastic part and then damage part. And the elastic part includes part due to the external load and the internal part. The internal part is then split into one positive part, negative, this one due to the tension, this one due to the compression. Only the tension part is multiplied by a damage function, which has to fulfill the following conditions. And one typical example is here is a quadratic function. And of course, there are other suggestions instead. The second part is related to the damage. This part here is the standard part, and it's suggested by Frankfurt and Nier. And the other one is actually kind of regularization and has to stipulate that damage is an inverse, so irreversible process. So of course, now you can see we have a potential which is going back to the phase field method because we have neural network phase deep energy method, and we have a method which can help us to simulate the damage. For the first example, I choose some standard benchmark problem where we have a notched brittle plate, and we try to see what is actually what neural networks can do in this case. So you can see the results which we got. So nothing surprising, actually, what we can expect. So here you can see the propagation, the back propagation for the different time steps for different state of external load. We also check these results, so this benchmark problem, by comparing the results for deep energy method and finite element method for displacement in both directions, X and Y. And as you can see, actually the agreement is very well. However, there were some problems, as you all, most of you know, the neural networks are not always able to recognize the physical solution. So in some cases, the neural networks offer some completely unexpected possibilities. And one other disadvantage, for example, that when tries to produce unlimited negative loss. So we had to improve this basic formulation of the problem, and we did that by introducing a kind of post-processing where we add additional information to the deep energy method about the connectivity of correlation functions, and we did a kind of interpolation. So we produced not anymore discrete values for displacement, but we reconstructed the displacement and damage field by using standard shape functions. So then you can see here the results. So in this case, we were able to simulate much more complex configurations, and for example, to reconstruct the damage and the crack propagation in the case of a plate with several holes, where we have a mixed mode of fracture. Again, here you can see also comparison with the finite element method and displacement in both directions. So in the next part of the talk, I would like to tell about something about another problem. This is the solution of the wave equation, which is of course followed here by the boundary conditions and the initial conditions. And in order to suggest the appropriate NN model, we started with an analytical solution, which is actually based in these boundary conditions and about the claim by displacement conditions. And then we concentrated on a simple case, namely for the case that initial velocities are equal to 0. And we replaced the boundary conditions by a kind of Fourier transformation. And in that case, one has an analytical solution also in the form of a series or expansion in terms of trigonometric functions. So our idea then was to suggest a neural architecture. We call that oscillatory physics informed neural network. We choose such kind of activation functions here, such that we can reconstruct the solution of this type. One that goes back to the eigenfrequencies in the last part, actually, to the excitation force. It is also important here, you can see that we have here a kind of error function which includes several parts. It's again not the mean square error function. We have something that goes back to the error due to the partial differential equation, error going back to the boundary condition, initial conditions, and of course we can implement some other terms. One of them was, for example, energy consistence. The last remark, actually, we also can use, for example, kind of post-processing to prove the suggestion of the solution, similarly as in the deep energy method, such that, for example, boundary conditions are introduced as a kind of post-processing step. And then the application of this model, I would like to show as a simple, very simple but challenging example. We consider here a bar longitudinal oscillation for the case that we have described only the initial displacement in the very first moment. And now I can tell why this example is very challenging, because the displacements in this case are discontinuous. And you can see here, for example, analytical solution. It needs a very high number of terms in order to appropriately approximate this peak. And we are very lucky, for example, that our model, which suggests that is also able to recognize and depict this kind of behavior. Moreover, we had a very nice property here that our amplitudes are constant, so they do not decay over the time. This amplitude decay is actually characteristic and is not called actually the numerical damping. And this is one of most important disadvantages of classical solvers. Another advantage of this neural network method is that it can also be applied for very stiff problems where, for example, traditional methods completely fail. That's the green line. Our solution is actually given in the yellow color, and it has a very good agreement with the analytical solution in that case. Finally, I also would like to tell a few words about the evaluation of effective values for heterogeneous materials. Namely, I will not go here in details. In order to calculate the effective values, effective elasticity tensor, we have to use or evaluate the terms which depends on so-called perturbation of the elasticity tensor. And for the evaluation of this statistical average, we need so-called correlation functions, which we now try to reconstruct by using neural networks. So for first information, I need to know how these correlation functions look like. We choose here two examples. So here we have a heterogeneous materials with a small number of large inclusions, and here heterogeneous material with a large number of small inclusions. Here the correlation functions have a very smooth behavior, but here rather one wavy behavior. And this is a challenge for numerical determination of these functions. So another challenge is as well that we have to connect two types of data. Actually, we have to analyze the image and to provide the function as a result, so that we suggest several different neural network types. I will show only two of them here. One, for example, used a convolutional neural network to elaborate and analyze the picture. The other one is fully connected neural network. It has X is certain distances, input of correlation functions. By adding them, we were able, for example, to reconstruct correlation functions with the following quality. So the blue one is the reference, and the yellow one is an solution. So the solution is pretty well, however, is still not able to catch all the wavy character in some cases. And for that reason, we suggested, for example, as our last model, that the outputs of these two branches are multiplied to each other. This is so-called model operator structure. And we got in that case really beautiful results where the agreement between the reference solution and the N-based solution is almost perfect. The maximal difference is always less than 1%. So with this, actually, I came into the end of this presentation where I showed 3 examples. Of course, there are a lot of things which can be done since the application of neural networks for solution of this solid mechanics task is pretty new topic. Thank you very much for your attention.